Hi everyone, welcome back to the channel. Today I have something exciting for you. I'm going to be talking about Markov chains. And the picture that I have here, this diagram, is showing a very simplified version of the inside of a grocery store. And so I want you to, for a moment, imagine that you're inside the grocery store and there are four possible locations that you can visit. One is the produce department, where you have fruits and vegetables. The other is the pharmacy. You can also go to frozen foods or packaged foods, which might be all the snacks in the middle aisles and stuff like that. At each state or department in this case, you can move to another department. So I know they're all together basically, but imagine that they're all separate. So from the produce department, you can go to the pharmacy. And from the pharmacy, you can go to frozen foods. And from frozen foods, you could go to packaged foods and then go back to the produce department or back to frozen foods or to the pharmacy or whatever. You can move around inside the store. The important thing here is that there is a probability associated with each move or transition. And so as you transition from one state to another, there's a likelihood associated with that. And there are people that do studies on the movement of customers in stores. And so what we have here is a system that is describing the movement of a shopper inside of a grocery store. And it's described in probabilistic terms. And if you were to take all of the possible movements, which are not represented here, including coming into and leaving the store, if you take all of those probabilities of transition, you can create what's known as a transition matrix that summarizes all of that information. And that information can be studied as part of an analysis of this system called a Markov chain. And I wanted to show you really quickly, so I'll just drag this window over here. There's a paper relatively recently called a shopping path length estimation using Markov chain-based shopper dynamics model. Okay, so what happened in this study, apologies for scrolling down here, but what happened here is they actually have a similar map showing a graph of the entrance and the exit, as well as a number of different nodes or possible states where the customers might go. And then you can see that there are transitions between all of these different states. So these paths that can take place are modeled here. Now you'll know there's not one from 1 to 5 or 5 to 9, for example. But it is possible to come into the store from 0 to 1, move to 4, then arrive at 5, and then go back to 4, and then exit the store. And that would represent a complete path. And so this study is looking at the length of those paths. And as you might imagine, the more time you spend in the store, the longer that path will be, and the more money you'll spend. So there's obviously, an interest in the business to look at how long people are spending in the store and how long their shopping paths are as an estimator of maybe how much money they'll spend. So back to the grocery example, this is a very simplified version, but essentially the same idea is here, that we have departments or these states, and then we have a transition between them and a probability associated with each transition. So with that said, we're going to jump into a Markov chain problem of a different type. And for that, I have built a simulation. It's an interactive created with R and Shiny, which is some tool that allows you to do really interesting interactives. So we'll jump over to that and dive in next. Okay, so the simulation that I created, I'm just calling it Markov Chain Simulation, Gambler's Ruin. It's based on a math thesis by Fariha Mahfouz, and it was written in 2021 for a thesis at the University of Texas, Tyler. And the idea here, and this is a problem that can be found online, you can read more about it, but the problem here is that there is a gambler who has a starting amount of money and is playing a game. And in the game, the gambler can lose $1 at a time until they have no money left, or they can win $1 at a time until they reach the maximum amount. And so the idea is that in each round they bet and then they win or lose with some probability. And so they can move up or down. And in this case, the chain is more of a linear layout, and we'll see that in a moment. But in this simulation, what you can do is adjust the variables associated with the game and then run the simulation some number of times until you reach a steady state. And that's the idea behind these chains often is that you want to maybe look at the long-term probability of being associated with one particular state or another. These are often used for analyzing how customers are loyal to a particular brand or not. So maybe you like one brand of drink and then you end up switching to another, but then you come back, or maybe you stay with one forever for some reason. So those switches, those changes, those transitions have a probability associated with them. And of course, those brands are interested to know how likely customers are to be loyal to their brand or to change to another competitor. But anyways, back to this idea. So we have a gambler who is putting down a dollar bet each time, and then they can move up or down. And there's a probability associated with that. And so if we look at the simulation inputs, we can adjust the starting balance, which is how much money is in the hands of the gambler at the beginning. Then we can look at the winning balance and change that value. That's the upper limit when the game ends. The rounds of gambling is how many times the simulation runs. And the probability of winning is, how likely they are to move up by $1. Below that, we have a graphic representation of the states and their changes. So very quickly here, in this given network, you can see that 0 loops to itself, meaning once you have $0, you are staying there. And you notice there is no arrow from 0 to 1. You cannot go in that direction because you can't bet with no money. If you have $1, you can lose it and go to 0, or win and go to 2. 2 can go down to 1 or up to 3. And then 3, because it's the highest amount in this case, can only loop to itself and not go back down to 2 because the game ends when you win the most money. A summary is given here, so you can just recap the values. There's a button to run the simulation and gamble. In the middle column, we have several matrices, and the first one is the transition matrix, which describes all of those changes. So in this particular case, 0 loops to itself. We can see that in the diagram. So that has a probability of 1, and that column of values sums to 1. 1 can go to 0 or 2, and so the probability of winning here is 0.58, which we have set. And the probability of losing is 1 minus the probability of winning, so that value is 0.42. And those also sum to 1. For the 2 column, we have a similar situation, except in this case, 2 can go to 1 or 3, and then 3 loops to itself and again has a probability of 1 because it's stuck in that state. The gambler's vector is indicating the amount of money that the gambler has at the beginning. And this will be updated as part of the simulation to produce the output vector, which we'll look at in a moment. But here we can see that the gambler's vector is described in the column of this table, and you'll notice that it is 0, 1, 0, 0. That indicates that the gambler starts with $1 because this 1 is in that position. The 1 itself is not the value of the money. It simply indicates the position in this list of numbers. And you'll see this 1.00 move positions as you change the starting balance. So for example, if I move it to 2, you'll see that it ends up here in the 2 spot. So that position moves around. So this is what would be known as a one-hot vector, where everything is 0 except for that single position. Now, when we run this simulation, we end up with a final output here. And it's just called V1. I didn't change that, but that's the output vector. And what we see is a probability associated with each of these values. So the first one is 0, and so there's a probability of 0.11. There's a probability of 0.79 for the winning value. So in this case, the long-term probability is that you would end up winning the game. If you were to start with $3 and go through 5 rounds of betting. So there's a good chance you would end up winning the game. And you can notice that the network here has been updated as well. If you were to do 5 rounds of gambling and you had a winning, a balance of 6 for the maximum there, and you started with, say, $1, this is the transition matrix, which you can see is much larger now, but it follows the same pattern. We have a combination of winning and losing probabilities for each of those transitions. The gambler's vector has a 1 in the $1 position, and then we can run that and get the output vector, which shows a 57% probability here for losing, actually, for ending up with $0. If you, however, change your starting balance to a much higher value, instead of starting with $1, let's say you start with $5, we can rerun that and see how that affects the probability of you winning the game. That is, we're looking for a specific change to raise this 7% in the last part of that vector to a better number. And if you look at this, we can see that it actually raises that to close to an 80%. And so that indicates that starting with that higher dollar amount will get you much closer to winning the game, which is where you want to be. And so if we look, there's a little interpretation, and this was given in that thesis. This vector contains the probabilities of having each associated amount of money left over. So in this case, that last value represents the highest amount of money that you can win. And so a high probability of having $0 is a losing strategy. But in this case, that's only at 1%. A high probability of having the maximum number of dollars. So that suggests a winning strategy, and that's what we have here. So if we start with a lot of money and a relatively good winning percentage of 0.58, then we're likely to win. And so in this simulation, you're encouraged to try adjusting these different values to learn the effect of maybe starting with less money or more money given a certain winning probability. And so we could change that too. We could also lower the probability of winning to 0.21 to make it a lot harder game. And if we were to gamble with that, we can see that the likelihood of losing is 0.31 and the likelihood of winning is slightly less. So they're almost the same, but there's also a relatively frequent, relatively here, because they're all about the same, for $2. So 0 is 0.31 and $2 is 0.33. So you might not have a whole lot of money. And in that case, you would continue until you ended up at 0 or the max. So in any case, this is an interesting way to explore this problem in that you can adjust the variables and use this simulation to generate your own data and then ask interesting questions and research them yourself to come up with an answer. So I hope you enjoyed this, and please consider liking and subscribing to stay tuned for more ideas.